hardware software integration project in Vivado. Essentially, this is going to be just if you go into the embedded system for PSoC tutorial, right? This is tutorial number 2. Okay, you will need this for, say, lab number 1. Okay. This topic, of course, hardware-software integration, is being covered in unit number 5 in the class, right? Okay, so the procedure, of course, is laid out in the tutorial number 2, right here. Okay, all that I'm gonna do in this video is just covering, the steps in this tutorial. Okay. Let's see, what else do we need to cover, or what else do I need to mention? I think that should be it. Okay. Oh, something else. I am gonna do this for the ZYBO Z710. Okay. For the normal ZYBO board, the procedure is almost identical. It's only one file that you need to have differently. Okay, everything else is going to be the same. Okay, so let's get started. Okay, this is, like I said, a very hands-on experiment, and you will need it again for your lab number 1. If these steps are confusing to you, and if you want to know more about this, let me refer you to the following material. This tutorial right here is essentially being covered in the Sync book tutorials. You have access to this book. It's, I think, this one here. This unit, First Designs on Sync. Okay, and it will go, step by step through all of them. Okay, so let me mention this. Based on one is called First Designs on Sync. Okay. Okay. So before we start, let me just quickly tell you the following. Again, if you go to the Sync book, right, it will show you what is the device we're working on. So the device we're working on is called the Sync 7000 PSoC. That means Programmable System on Chip. That includes an ARM microprocessor plus an FPGA. Okay. Whereas the ARM microprocessor and a bunch of other peripherals, they are called by I guess it is just a fancy name, PS, the processing system, and the FPGA is called PL, the programmable logic. Okay, and the chip is right here. At least a general block diagram. The PS, of course, is hardwired, right? But the PL, that's where you can reconfigure your hardware. Okay. And to connect these two, we use what I call the AXI bus. I think it stands for Advanced Extensible Interface. Okay. So ideally, what happens is the following: you design your hardware on the PL. You add your then you add your AXI interface, then integrate hardware with SoC. Okay. Usually, the way you design your hardware, Of course, you can do it on your own. That will be custom. Well, we have to call that custom peripherals. And by the way, that applies, of course, to everything. Let me show you what I mean by that. That you have to design your hardware on the PL, and also you have to design your own AXI interface. I mean, your interface to the AXI bus. Okay, that you have to design. However, the way we're going to do it in this class is the following. What we want to reach eventually is the ability to be able to build our own custom hardware, right, with our own AXI interface. That's what we are going to do. In fact, that's what we will do in the labs, I think, in the next labs, by the way. However, in this tutorial, right, we're going to take a shortcut, and instead we're going to use a pre-designed hardware component, and pre-designed actually by Xilinx, by the manufacturer. Okay, and of course the procedure is significantly simpler because the hardware code and its AXI interface is already available. The one we're going to use in particular is called AXI General Purpose I/O. Again, it is just a fancy name. It is no more than registers. I think only 2 registers. Of course, registers plus an AXI interface. Okay. So this is what we are going to do today. So just to give you an idea, of what's going on. Okay. And of course, once we complete this project, we're going to have to create the software part, right? So let me see. The design of the hardware on the PL, including the AXI interface, you do it in Vivado. Okay. The integration also happens in Vivado. But after that, you have the software routine. I mean, where do you you have to develop, right, your software routine. Not only that, you also need to test your software routine. That is now gonna be taken care of by the following software, which is called SDK. Okay. And that's, I think, a summary of what we're going to do today. So let's get started. We're going to first open a new Vivado project, and we're going to integrate hardware and software, because the hardware we already have it, because it is a pre-designed component by Xilinx. Okay. So let me get started. Let me see. So you open Vivado, right? And what I'm gonna do is just, like I said, you can complete this, of course, by just following the tutorial too, by the way. Right here. Okay. I mean, here you can see a bunch of files, but the only ones you're gonna need is the ZYBO master file and this software file. Okay. I'm gonna go very easy in this. Let me do this then. So the first thing I gotta do is to create a folder for my project, and I am gonna call it, right, my first zinc sun. To be fair, the name doesn't really matter here. It's not really that important. Okay. So like I said here, there are many ways to specify what we call the XML definition files. I mean, if you're curious, read about this, but I hope all of you have already followed this procedure that is detailed in the class notes. Okay, in the class website there is a link for it. Okay, on how to do it. It is just copy and paste, a folder, right, onto a particular folder in the installation directory of Vivado. So we're going to follow this one, where we install the board files for Vivado. Let me mention it here. We assume you have installed the definition files for the not only the ZYBO C710 but also the normal ZYBO and others actually boards. Okay? Like I said, by default Vivado has a bunch of boards already defined, but for some reason it does not include the ZYBO, for example. So you have to do it manually, but only once, okay? Only once. Okay? If you want to know how to do it, it's right here. Okay? So that's the first thing that you have to do. Then, of course, we're gonna continue. Let's skip this part because this part is the old method, okay? The 1A method. We're doing right now the 1B method when actually you have installed the files in Vivado already. Okay, that's the 1B method right here. Okay, so we're gonna create a new project. First, sync design. Okay, and I'm gonna go through all of these steps one by one. Okay, so that's what we're gonna do now. So let me create a project. My Vivado is a bit slow. Just please have some patience here. So now we got, of course, I mean, you can place, this folder wherever you want. I am just using a particular folder for it. Just give it a moment. Okay, here we go. So my idea is to use this folder first, sync design. So first sync. Again, just continue. I mean, you don't have to worry about all of this. Keep going. Make sure though, one thing that you have to make sure, of course, when you create it is that the target language is in VHDL. Okay. No constraints yet. And here, of course, you have to select on boards. You have to go to ZYBO. If you have installed the your board right properly, it should appear in this list, and you just select ZYBO. Here now, remember, unlike a previous tutorial, here it is very important that you select the right board. Oh, I'm sorry, right? I'm using the ZYBO C710. See, I almost forgot about it. ZYBO Z710. Okay. So, if you read through the tutorial, you will find out that all we do is control LEDs via software. Remember, the LEDs are only accessible through the programmable logic, okay? To the PL, which means that they are not accessible to, I mean, you can't do that with just pure software. You have to have integrated software and hardware. So that's what we're going to do, just control the LEDs to refer. That's all we need to do. So, and because we are controlling something that is accessible only through the PL, we need to include, remember, the XDC file of the board. In this case, is the ZYBO C710. Okay. So once you create this, right, according to the tutorial, right, what you need to do is to copy and paste the definition file. This is the file that you would need for the ZYBO, and this is the file that you need for the ZYBO Z710. That is the only difference, okay? And that's all that you have to do to refer, okay? So now we're gonna actually, of course, I already have the files. I'm gonna just open this and copy and paste that file right into the folder structure. Okay. So then, what do we have to do now? A moment. Here we go. So there are a bunch of steps here, so we have to follow them one by one. Okay. So like I said, this component, this AXI GPIO peripheral, is a block that has been already created by Xilinx, and it is very easy to integrate because it has already been pre-defined. Okay, you will see all that you will be doing is just click, 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 click. Okay, I am gonna try to explain, what's going on, at every step of the way as I can. So the first thing we gotta do, again, let me see if I forgot, we have to add the ZYBO XDC file into the project. So remember how to do this. You do add sources, constraints of course, add files, and you look for that specific file, ZYBO Z710, or Z7 if you like. Okay, and there you go. Okay, of course the file is you would say empty or blanked out if you like. There is nothing there yet. Okay. Oh, I think I probably, let me see. This is probably a mistake that I made somehow. Sorry about that. It's supposed to be completely commented out. Okay, the whole thing. Okay, so let's continue now. So here is what you have to do. We have to now, since we have the hardware and component already developed, right? We have to now integrate the hardware with the microprocessor system, and that's a really easy step. You have to create a block design. It will open a white canvas, and it will let you, interconnect block designs, your block and the microprocessor system. Okay, so let me take a look. I hope it is a bit slow, unfortunately. Okay, so once we do that, you get here a white canvas. So what do? You have to add components. All you do is you right click and then add IP, and then as you follow this thing, right? You first you have to connect the PS, which is the the microprocessor system, right? And then you connect the AXI GPIO. Okay, so this is what we're gonna do now. We're gonna have to look for it. I think if you look for sync, there you go, sync PS processing system. Then you double click. Okay. Give it a little bit of time, and it will pop up. At this stage, it's actually very easy. It's just a click and follow. It's not really hard. I mean, the really difficult part is when you design your own custom peripherals. Okay, so here you gotta run something called run block automation, such that the processing system, right, includes now pings, I/O pings to the DDR memory and the input-output components controlled by the PS. All you have to do is click there and then just click. That's all. You will create an interface for the external circuitry for the PS. Okay, so that is the first step that you gotta do. And here is the interesting step, because so far we only have the PS, just the software component. Now we have to add our hardware block, which of course is called GPIO. It's already there. By the way, there are many that are here available by Silos. Okay, there are many, but of course you have to know how to work with each of them. It's not that straightforward. Now the question is how you're going to interconnect them. There are many ways, but let's go by the easy way. And let's leave it to the software to do it for us. Okay? So, this is very easy. We're going to do the following. Run connection automation. It is going to interconnect those two using an AXI bus. See, you have to click on all of them. One important part, and this is not, by the way, very important, and it's already, by the way, mentioned in the tutorial. You have to configure the GPIO, because as the name implies, this is general purpose input and output, which means that can be an input or an output, right? And you have to configure what this is. So you have to click here on GPIO, and you have to just click on what you want. You want to use the 4 buttons, remember, of the ZYBO board or the HDMI. You know, there are a lot of interfaces. Since we plan to control the LEDs, the 4 LEDs, right? We just click on the LEDs 4 bits. Okay. Apparently, on the ZYBO Z710, there are some RGB LEDs, just in case you want to know. I don't think the ZYBO has that, but it doesn't really matter, because for what we are going to do, this is going to be irrelevant. There you go. Let's 4 bits, and that's all, actually. And once you do that, you will see that everything will be connected. Okay, there you go. So here you can see, for example, the processing system, the peripherals, the hardware, right? And these two components are the interconnection. For example, here, this block here is the AXI bus system, interconnecting the PS and the general purpose I/O, which is just, by the way, as I said, is a bunch of registers. And then for some reason, this is the PS, right? That's what we call the reset system. For some reason, this chip has an entire circuitry for reset. Based on the external reset, it issues a bunch of different resets. Okay, you can use, I think, you see, regenerate layout, so you can have a nicer layout. Okay, what else do we have according to the tutorial? Well, just to let you know, of course, as an interface, we have the 4 LEDs, right, that we plan to control. Let's say, what if we double click here? What are we gonna get? You will see this. So every Sync 7000 chip has this. But look at this. Look at here. Look at these check marks. Okay, like UART, GPIO, SD card, USB, Ethernet, memory, quad, SPI. Okay, the ones who are checked, those are what we call the available resources on the ZYBO 710 board. Okay, your chip, the Zinc 7000, includes all of these resources, by the way, even the CAN, for example, a CAN bus interface. However, your board, right, needs to support externally, right, those interfaces. So, well, your ZYBO board does not support a CAN interface, for example. It only supports a UART, a GPIO, SD card, a USB, an Ethernet, and a quad SPI. Okay, these are the peripherals controlled by the PS. Okay, so this is in case you want to know, of course, what's going on. Okay. Okay, so just close it for now. So this is a good overview. Well, it's mentioned here, right, which peripherals are available. Okay. Remember, the chip has all of the peripherals available. It is the board that indicates which ones are the ones that are supported. Okay. So now, what do we do? So now it comes the relatively tricky part, right? Let me see if I got it here the right way. If I made a mistake here, I don't think so. Let me see. Okay, so now we have to create something called the HDL wrap. And in this case, of course, they call it HDL because it can be either Verilog HDL or VHDL. So what do we do here? It's essentially a VHDL file that will have these components interconnected together. Okay, so we have to go to source. You see this, golden tree here. You right click and then you do create HDL wrap, and then you just click OK. Okay, let's give it a moment. Takes a little bit. Okay. Don't mind these warnings. This is just some memory warnings. I think it's just sort of a bug in the software. But now, let me see. We're supposed to be good. Just give it a little bit of time. Should work in a moment. There you go. So now we have actually a VHDL file that is the wrapper, that wraps everything right together. And if you open it, you will see here that this is like the input and output of your entire system, right? There are inputs, components for the DDR, for the IOs of the particular PS, and of course your LEDs, which have this name, LEDs 4 bits 3 IO. Okay, and of course here on the architecture is just what? It's just remember the port mapping. It's just interconnecting all of these components. What else I can tell you from now? We will explore, by the way, this later. Your peripheral, of course, has a memory address range, in the for the microprocessor. Okay, but we will cover that later. Okay, so with that, are we ready to proceed? Are we ready to create, the bit stream? Not yet. This is the part that you have to do it manually. You have here the LEDs. So remember, these LEDs that we have created, right? That we have created, manually. We have to now indicate them also manually in the master file, XDC. Okay. Remember, you don't have to indicate anything else. It is just the LEDs. Somebody might be asking, well, but I see there are a lot of input and output ports here. Well, don't worry. The Vivado will take care of that on its own. It is just that the ones that come from the PL, from the programmable logic, those are the ones that you need to specify directly on an XDC file. Okay, so let's do that then. So the name is LED 0123. Well, we're gonna replace it by, remember what was it? LEDs 4 bits 3 IO. Because remember, they have to match, right? Exactly. And we have only 4 of them, of course. We use 4 of them. Okay. And there you go. Now we save it, and now, in theory, we are ready to go. Let me see. We have to now, do what you know already: synthesize and implement and generate the bitstream. So give it a little bit. We're gonna now run synthesis. Hopefully, we did not make any mistake, but who knows, right? There is a possibility always. Just give it a little bit. Okay, after a little while, the synthesis completed. So what is the next step is to run implementation and then generate the bitstream. We can just directly jump into generate the bitstream because it will run this in first. Okay, let's double check. I mean, I think everything should be fine, but yeah, I think we're fine. Okay, let's generate the bitstream. Okay, again, this will take a little while to complete. Okay, and the bit stream generation completed at this point, so we are ready. So in theory, we are ready to program, you know, the board, right? But the problem is that all the control is not through the PL, right? All the control is through the PS. So we need to download some software code in the PS such that it controls the LEDs. Okay, so we have the bitstream ready. That's one piece of information. Let me just make sure this point is clear. So for hardware, for the PL, what we have is a .bit, what we call the bitstream. But for software, for the PS, we need to get, in this case it's called ELF. It's an executable file. Okay, and this is what we need to do now. Sorry, just a moment. So according to the tutorial, of course, you have to export your hardware and then open the SDK. Export means we're going to copy the bitstream onto SDK such that we can program our board from SDK. SDK is a different piece of software, by the way. So how do we do that? Well, here, File, Export, Export Hardware. Make sure to also, of course, check here, include the bitstream. There you go. That's all. Once you complete that, now you have to do the following. You launch SDK. Before I say anything else, just be careful here. Let me say the following. Remember your folder here, right? The moment you export to your hardware, this folder .sdk, that is where your software project will be stored. Okay. So far, the only thing that is here is a reference to the bitstream, of course, to the hardware. Okay. So now we're going to launch a SDK. Again, everything should be local to project, and in a little while you will launch the software. Okay. It will take a little while probably. And as you can see, you know the folder, the SDK project folder is starting to be populated. Okay, so here is the SDK, and bring it to this window. It's still, working through the motions. It's gonna do more in a moment. It's gonna provide you with entire software repositories. Okay. Okay, so this by the way is going to take a little while as well. Okay. So this is the interface that you are gonna get. Okay, this is the address map for all of the peripherals. Don't worry, as we will go over the material, in further sections, we will learn more of this. For now, the important part here is, of course, this window problem, which is the list of software errors you might have. Also, the SDK terminal, we will use a serial interface, a UART, to interface the ZYBO 710 board with my computer, and the messages will appear here. Okay. These two, what else do we need to know? Well, to start a project, what we do is simple: new application project, and you can call it, if you like, LED test. To make it simple, in this class we're going to just use simple C. And here there is something else called the board support package. It is just a bunch of drivers, right, for every peripheral that you have in the board, including the AXI GPIO that we just integrated. So then you go to next. Here you will find here a bunch of different examples, but I always select here the empty application, and then I let it finish. Okay. It's gonna take a while again to complete. So ideally, you of course you have to create a new C file and then just start typing your software code, right? But of course, instead I already have, and of course this is already available to you, by the way, in the tutorial number 2, this file, which is a file that I'm going to run. Okay, so give it a little bit, let's see where we're at. Yeah, again, it's taking a little bit, just okay. I think it's ready. How do you know it's ready? Because your project folder, LED test, and the board support package, which is the drivers, are here. You can just, of course, open them. For example, your board support package here has a bunch of files, right? A lot of libraries for every peripheral that you can think of. Okay? We're going to use in this class some of them. We're not going to cover all of them. And your LED test, has a bunch of source files. These are just configuration files. There is nothing here. So ideally, you would have to create a new C file, right? By the way I'm going to do it, I think I stuck, doing this. I'm sure there are better ways of doing this. All I did to do now is the following. I copy this file, and then I go into my SDK folder, and you will find here, you see LED test, the software project, and then to source, and I just copy. I am sure there are fancier ways of doing this, but so far this is what I am used to now. So then this part, I guess, is a part that the first time I got a bit confused. So we have to refresh to update these files. Look at this. My folder is not here, so what I have to do is right click, I think, and refresh, or F5, and it will just not only update the list of files, but it will also automatically, because this is how SDK is set up, at least in this last version, it will automatically start compiling all the code. As you can see here, by default, the build automatically is set up. So every time you add a new C file, or every time you edit a C file, it will automatically build. Okay, you might turn it off such that you only build or compiled when you want. Okay, keep that in mind. Okay, so this thing again is going to take a little bit. Okay, like I said, fair warning. For some reason, in my opinion, in the last 2 versions of Vivado, the compiling of the C file takes, a lot of time for some reason. I think it's a bug of the software, because it didn't used to be like that at all. So this is your file. Once everything has been compiled, let me show you very quickly. Simple includes. This is the driver for the GPIO and so on. It's a simple function here, and all it does is it initializes the GPIO, and then it sets their direction, right, to be output. And then we're in a while loop. In a while loop, what happens? We write a particular number onto the LED. For example, what do we write? We write the variable LED. And at the beginning, LED is what? 099, which is 1001. And then we flipped the LEDs, and then we have a software delay here. Right, this is the delay. I don't know how much it is, by the way. And then we start over, we write again, but we write what? The inverted version. So essentially, you will see the idea is that you should see your LEDs blinking like this, right? 0110 to 1001 and so on. Okay. On top of that, this function here, because it is executed here, before doing that, I am gonna print a message. So now when we execute the command printf right here, what would happen is it will be printed on the UART. Okay. Printed, I guess, quote unquote, printed on a serial port using the UART. Okay. So, of course, the UART is a very old, communication protocol, but it is implemented in your board, right, using the USB connector. Okay. Okay. So that should be all. So now, what are we gonna do? What we need to do is to test. Now we're ready to test, and the way we do it is like this. The first thing that you gotta do according to this, let me see if I got it right or not. Okay, the first thing we have to do is to download the bitstream. You go here and then you program the FPGA. Right? They remember the .bat file, so we program the hardware. Here we go. Unless something was very wrong, this should work fine. And there you go. And my board now is programmed. When it is programmed, that's actually when the UART interface has been enabled. Okay, on the on my chip, and my computer should recognize it. So before we load the software, we have to make sure that my SDK terminal, my serial terminal, is configured properly. All we do is we add here, and we have to look for the proper port. Which port? Well, you can always go to the device manager and see which one was the latest COM port that was added. But by default, once you program the FPGA, it will show you here, COM10. So you don't have to do anything. What about the baud rate? This is the one by default, and of course it has to match the one on your hardware. How do we verify this? I think if we double click here, I think, if I am not mistaken, you see, we should be able to find that. Okay, maybe just give me a moment here. Okay. So you go to the PSPL configuration, for example, you go to General, and you will see here the UART baud rate is 115200. If you change this, well, you gotta make sure that when you use the SDK, you use the same baud rate, of course. Okay? So now we say OK, and now we're ready to hopefully, see the printed message. So the moment we program, we are supposed to see the LEDs blinking, and we're supposed to see the message here. Okay, so how do we program it? Remember, what we have to do is to include this file, the ELF. That's the executable file. Okay, and I think you should be able to see it here. Let me see. If you go to LED test and then to debug, that is the executable file. Okay. Again, how do you compile? Let's say you made a change here. How do you compile? Well, it will be automatic, by the way, every time you save it. But if you, of course, uncheck this line, you will have to build build your particular project. Okay. So how do we load the software? We right click on this project, right, and then we do the following. Let me see. Run as, and then hopefully everything will be okay. You never know. Sometimes these things, there are mistakes here. Let's see. Launching hardware. It's gonna take a little bit. And here we go. So I don't know if you see it, but here you can hear ECE 5736 and it says GPIO output test. So we are confident that this part is working. I guess I can see right now that the lights are, are on. Okay. Let me see. Maybe I can show this to you. I don't know if I can, but okay. Just give me a moment, okay? I will show you this. Well, as I was saying, this is the LEDs blinking, right, on our software application. As you can see, we are able to control the LEDs states via software, okay? Right. Thank you so much, and please, I hope you can try this on your own boards. Thank you.